right, let's go ahead and let's get into it. So your homework is on page 130, technically at the top. So questions 4 through 7. All right, so what term refers to, was it 1 through 7 or 4 through 6? Let me check really quick. 4 through 6, I'm sorry, 4 through 6, the top of page 130. If you already did number 7, good for you. But at the top of page 130, let me double check one more time. Yep, it's 4 through 6. So sorry, I accidentally said 4 through 7. Sorry about that. So 4 through 6. So what process splits down to nucleus to produce enormous amounts of heat, energy, and gamma rays? All right, that is nuclear fission. It kind of rhymes with division, so that might help you to remember it. Number 5, what term refers to the amount of fissionable material required for a chain reaction to occur? That is critical mass. And then number 6, what is the device that harnesses a controlled nuclear chain reaction to produce useful energy? That is a nuclear reactor. We will talk more about that as we get to that section. All right, so as you remember, what is today? The periodic table quiz. So if you want to pause the video because you realize, ooh, you forgot, then go ahead and pause the video, study it for about 5 to 10 minutes. I'm going to study with you. I'm going to drill with you one more time as well before you take it. So pause the video if you need to for about 5 minutes. If you want to try to cram it, you can, but I'm going to go ahead and go over it with you as well. So if you want to study on your own really quick, you can. But let's go ahead and let's go over it. So you don't have any official classwork. Besides, if you want to cram really quick, go ahead and do so. All right, well, let's go ahead and let's go over them. So same thing as what we've been doing. I'm going to hold up a card, and I'm going to give you a second to try to say it. Try to beat me before I say it. We're going to go through them probably only one time, really quick. Just because you can pause and rewind the video, unless you're the live person watching with me. But if you want to go through and pause the video and then go back and rewind it and watch it a couple of times, you can. But I don't want to do it over and over and over again if you just have the ability to just rewind it yourself. So let's go ahead and let's do this really quick. All right, so SN, tin, Mg, magnesium, Ra, radium, Rn, radon, Hg, mercury, O, oxygen, Pb, lead, Ag, helium, Ba, barium, Kr, krypton, Au, gold, K, potassium, U, uranium, B, boron, Ar, argon, Ne, neon, Ca, calcium, H, hydrogen, Cu, copper, Al, aluminum, C, carbon, I, iodine, Fe, iron, Na, sodium, N, head is upside down for me, nitrogen, S, sulfur, W, tungsten, Cl, chlorine, nickel, I'm sorry, what I get for looking at the answer, Zn, zinc, As, arsenic, Si, silicon, Ag, silver, P, phosphorus, Zr, zirconium, and I, nickel. Alright, so if you realize now that you want another minute or so to go back and study over them one more time, you can. But make sure you pause the video. If you need to go tell your proctor or your parents or grandparents, whoever has the quiz, go ask them for it. Now remember, you don't want to have anything on your desk or table or wherever it is you're taking this at. Don't have your book open, don't have your book out, put your cell phone away. You only need a pencil, well, technically a pen. You only need a pen and then just the printed quiz. So go ahead and go pause the video. If you want to study for a minute, you can, but then put the book away and then go ask your proctor for the quiz. So go ahead and pause the video, study if you need to, take the quiz, and then once you come back, you can unpause the video. But make sure for your quiz that you read all of the instructions. The quiz necessarily isn't very hard, but pay attention and be sure to read all of your instructions and all of your choices. Don't just go through it too fast. So be sure to take your time as you're doing it. should write your name at the top and the date so I know who's who whenever your parents send it in, whenever I print them off. So make sure you go ahead, you study for a minute, but then go ahead and pause the video and then go ask your proctor for the quiz. Alright, assuming that you're still watching this now, that you come back and that you've taken the quiz, hopefully you did well, and hopefully you realized once you got started, oh, okay, this isn't that bad. So hopefully it was pretty easy and pretty straightforward, but you do need to know it for your test coming up as well. So don't just forget the periodic table. We're not going to spend as much time drilling them every single time anymore, but you do need to go over them and you do need to be studying them. So that way, for your test coming up, you'll still know them for it. But I hope you all did very well on your quiz, and I can't wait to get the quizzes back, because hopefully you realize this quiz wasn't too hard. So make sure though, make sure you give it to your proctor. So put it off to the side so that way you don't forget about it, and then give it to your proctor to email to me later. Alright, so you can go ahead and get out your textbook now. So let's go ahead and let's get into chapter 6. You didn't have any really classwork on the material in and of itself, but let's go ahead and let's start reviewing a little bit over it. Now, not necessarily just the periodic table, but just thinking over several of the terms and definitions. Like, for example, what determines the atomic number of the element? Remember, atomic number is the identity of the element. You know, just the number of protons. What charge does a proton have? Is it positive, negative, or neutral? A proton is positive. What about an electron? Is it positive, negative, or neutral? It's negative. And then what about a neutron? It is neutral. Which two parts, positive, negative, or electrons, are on the nucleus of the atom? They're the nucleons. Protons and neutrons. Good job. Alright, so can you have a different number of protons in an element? No, you cannot. You'll jump elements entirely. Can you have a different number of neutrons? Yes, you can. What do you call it? You have a different number of neutrons. An isotope. Can you have a different number of electrons? Yes, you can. What do you call it if you have more electrons? What specifically? Remember, it's an ion, but what specifically do we call it if it has more electrons? Remember, if it has more electrons, it's going to have a positive charge. Right, so that is an anion. What if it has less electrons? So it has a positive charge. Cation. Perfect. So we've been talking about this for a couple days, so make sure that you know them really, really, really well. Alright, so thinking about the different scientists and what they discovered, who proposed the atomic theory? John Dalton. Who proposed the quantum theory? Who is that guy? Max Planck. So make a note for him. He said the quantum theory, that the electrons, if they're going from one energy shell to another, then they have to lose or gain energy. So he said that they have to lose it in these packets of energy. Now, who took the quantum theory and he made a better version of over what an atom looks like by saying that the electrons are locked into these orbits. So remember, we already talked about several different models, like John Dalton's model, how they're like a hard sphere. J.J. Thomson's model looks kind of like a plum pudding or kind of like a chocolate chip. Rutherford says that they all look like planets. While Bohr said, hey, what is it? I think I asked the name over who was the guy, and I just gave it away by accident. But he said with his theory that the Bohr model, they're locked into those orbits. Alright, so who came up with the wave mechanical model, saying that they move in this wave-like pattern as they go around it? Erwin Schrödinger, so make a note for his name as well. Alright, who came up with the uncertainty principle, saying you can't know the position and the velocity at the same time? You can know one or the other, but you can't know both at the exact same time. That was Werner or Werner. Sometimes you hear it pronounced with a V. Heisenberg. So make a note for him. So he came up with the Heisenberg uncertainty principle. Alright, who said, okay, between the wave mechanical model and the uncertainty principle, they're not locked into orbits, they're locked into these regions of space called orbitals. So who came up with that electron cloud model, saying, hey, they're locked into these regions of a high probability of finding them. So they do stay in those energy layers, but they're not locked in a straight line. They're moving up and down. And so because of that, it's a high region of finding them. So that was Max Born. So make a note for him. Alright, what do we call the numbers that represent the overall position of an electron? It's like the address for the electron. There's 4 numbers. What do we call those 4 numbers? Quantum numbers. Good job saying what energy level it's in, what shell it's, what energy level it's in, what the shape is, the orientation in space, and then is it the one electron or the other electron? We describe them with spins. Alright, what principle says that no 2 electrons in an atom can have the same 4 quantum numbers? You can't be in the exact same space at the exact same time. That you're going to have one in one side and one in the other. That's the Pauli exclusion principle. So just make a note of that. So Pauli exclusion principle. Alright, so you go ahead and open your textbook to page number 122 through 123. That's where we left off last class period. So the Pauli exclusion principle. So for this one, this is where we left off talking about the electron cloud model and the wave mechanical model. So going back a little bit. So this is the idea of the Bohr model, where he said that they're locked into these orbits and they can only go from one layer to another if they have that quantum of energy. So to move farther away, they need more energy. To move closer, they have to lose energy. This is an example of the Bohr model. Wave mechanical model, the idea they move in an up and down or a wave pattern as they're going around it. So the uncertainty principle says that you can either know the position or velocity. Your book uses the word velocity because your book hasn't introduced momentum yet, but momentum, velocity, and speed are all very similar ideas. They are distinctly different. But since your book hasn't talked about momentum yet, that's probably the reason why your book uses velocity. And then you have the electron cloud model with the idea of, okay, because they're moving up and down or on that wave pattern as they're moving, you don't know for sure where they're at, because remember, I can either know how fast they're moving or I can know where they're at and they're not moving anymore. So you said, okay, that means there's a high probability of finding electrons in a certain spot, and we call those orbitals. So not orbits anymore, because orbits has the idea of they're locked into a circle. Orbitals has the idea of it's in a region, so we're not sure where, but it's somewhere in this region. Probability contours are the shapes we draw around the regions to represent, hey, here's the region or the shape of the orbital. Whoops, too fast. So again, the quantum numbers, the first one tells you the shell, the second one tells you the orbital shape. You can have different types of shapes for them. We'll talk more about this in chemistry later on next year for some of you. You can talk about the orientation, is it back and forth, front and back, or up and down. And then also, each orbital can only hold 2 electrons, so we designate it as one spinning one direction, one spinning the other. So technically they're not like sphere spinning, but that's the idea, so it works. Alright, so make a note for that with the quantum numbers. Pauli exclusion principle says that no 2 electrons can have the same 4 quantum numbers. Remember, you can't exist in the same region of space as an object. So that's probably the reason why at the beginning of the year with volume, I tried to have Brecken go through the door whenever the door was closed. The door was dimming the space, and Brecken can't go through it because the door has already dimmed it. That's the same idea with the 4 quantum numbers. You can't have 2 electrons in the exact same space at the exact same time. You can have one be close to the other, but they can't be in the exact same space. Their electrons won't let them do that. So they can't exist in the same point in time. So that's probably the reason why you have one electron, then you have the other, and no 2 electrons have the same 4 quantum numbers because they can't exist at the exact same spot at the exact same time. Alright, we talked about changes in the nucleus and radioactive decay. Got into this really quick yesterday. Alright, so your book points out that some atoms, they are stable to where their nucleus doesn't change. Some atoms, their nucleus is unstable and it wants to break apart into smaller pieces, typically. So, whenever it says, most of the nuclei of atoms are stable, but the nuclei of some isotopes, now remember, what's an isotope? This is an element that has a different number of neutrons than normal, so make a note for that. So, when the nuclei of some isotopes are unstable, so they are capable of breaking up or otherwise changing into another type of atom. So make a note that's what an unstable isotope is. When an atomic nucleus breaks up or undergoes a change, it gives off nuclear radiation. Any substance that is unstable, we also describe it as radioactive. So a substance that is unstable, we describe it as radioactive. When you have the nucleus break up or undergoes a change, it gives off nuclear radiation. The process is called radioactive decay. So that's what this is talking about. So radioactive decay occurs whenever the atomic nucleus breaks up or changes emitting radiation. There are three basic types. Technically there's a fourth one, but there are three basic types of nuclear radiation. So be sure to mark them as we're going through it. Your book points out, for example, radium-226. Now, looking at it, radium has how many protons? 10. It does not have 226. So look on page 131 and find radium. How many, let's see, we are talking about radium. How many electrons does radium have? Find it. Radium has 88 protons. So if you go down, it's in that second column. So if you're looking up and down, so there's the first column and there's the second column. All the way down at the bottom of the second column, you have radium. So radium is radium has 88 number of protons. So radium's down there. All right. So this is radium-226. So if this 226, what does the 226 tell you? Whenever you see it written out like that, what do we call that? That's the mass number. Remember, the mass number, typically we write it like this, to where the number of protons is the atomic number that tells the identity of the element. The mass number is typically written on top. So 226, that's telling us the total number of protons and neutrons together. Which is a side note, if you have 88 protons and 226 protons and neutrons together, how many neutrons does it have? I haven't had my second cup of coffee yet, so I don't trust my math. Alright, so quick math if you have your calculator out, or if you want to do it in your head, that's fine. 226 minus 88 is what? 138 for neutrons. So just make sure that you're connecting all the ideas. You don't have to know the number of neutrons, I'm just pointing it out. Alright, so your book points out a single gram of radium 226, radioactive metal, decays into radon 222 at a rate of 37 billion atoms per second. So your book points out over the years, the percentages of radium-226 in the sample will decrease, and the percent of radon-222 will increase. All right, looking back on the periodic table on page 31, where is radon? This might take you a minute. Where's radon? Rn. Hopefully you knew that already. Radon has 86. So, protons. So, if it has a mass number in this example of, what was it, 222? 222. How many neutrons does radon have if it has 86 protons? Still don't trust my math. Pretty sure I know. Alright, so this one also has 136. So, 222 minus 86 equals 136. So, again, you don't have to know this, we're just getting practice with it. So, you're having the substance decompose or break down from radium-226, decays into radon-222. So, over time, it's breaking apart, and you're going to have more and more of the radon form and less of the radium. So scientists, they can measure this in a unit that they call the half-life. So make a note of this. And the decay rate of a substance can be stated as its half-life, or the length of time required for 1/2 the original substance to decay into a new substance. So let's say I start off with 16 grams of radium. Now the half-life says that okay, that a half-life, this is how long it takes for 1/2 the sample to decay from one type of substance into the next one. So what's half of 16? 8. Good job. This isn't hard, I know. So your book points out the half-life of radium is 1,600 years. So scientists can measure and figure out that, okay, if I start off with 16 grams, if I were to tell my great-great-great-great-great-great-great-great-great-great-great-grandchildren to now measure in 1,600 years how much radium do I have, I should only add 8 grams of it. That's when it's kind of a unit of measure to see how long does it take for 1/2 the substance to decrease and for to have 1/2 of the substance change over into the new element. So 1,600 years later, how much of the original radium should I have? If its half-life is 1,600 years, and a half-life tells you it takes the length of time it takes for 1/2 the substance to change over, let's see, how much of it will be left after another half-life has occurred? 4. Good job. And then 1,600 years later, someone's still around to measure it. This is a very long time at this point. How much of the original radium will I have left? 2. So yeah, now keep in mind, sometimes you hear stuff like this, whenever people talk about it, they use this as an example for evolution because scientists say, oh, well, if it takes 1,600 years for a substance to change from one element into another, then that means we can look at an element like carbon and we can calculate backwards and help prove that the Earth is millions and billions of years old. We're going to talk about the problems with that a little bit later on, but just make a note though that that using science like this is fine because scientists can tell that sometimes it does take a really long time for one half the substance to decay into a new substance. But since we don't know how much of that original substance we started with, we don't know how long that rock has been around. So even though scientists know how long it takes for one half the substance to decay, you can't go backwards because very rarely do we find a pure rock or a pure substance like that to where you can go all the way backwards and figure out, hey, was this a pure substance and figure out how old the rock is. There are several problems with that. You don't have to note them right now. Your book gets into it later on. But just make a note of that if you're looking at this and if you're a little bit worried about it, wondering, this sounds kind of weird and kind of like evolution. It's not. Just make a note that the scientists have figured out that, okay, the time it takes for one half the substance is to decay into the new substance is very, very, very long sometimes. But that doesn't mean that the Earth is really, really, really old. It's just the length of time it takes from one substance to decay into a new one. Alright, so make a note though that the decay rate of a substance is often stated as the half-life, or the length of time it takes from one half the original substance to decay into a new substance. Alright, so next page for us. 3 different types of radioactive decay. There's alpha decay, beta decay, and gamma decay. These are based off the Greek alphabet. So make a note for this one. So alpha decay, I cannot draw that symbol very well. It looks kind of like a fish. So make a note, that's the symbol for alpha decay. So make a note for that one. It occurs when an unstable atom ejects a clump of 2 protons and 2 neutrons. Alright, if it's 2 protons, what element is that? Helium. So remember, it's not hydrogen. Hydrogen only has 1 electron. So helium has 2 electrons. If you need to look in your book for it, I'm page 131, that's fine. So for this one, you have helium. I'm going to switch pieces of chalk because that was weird. It splintered. Alright, so you have helium with 2 protons. Now it says it's 2 protons and 2 neutrons. So what's the mass number then? 4. So this is an alpha particle. So sometimes you'll see it drawn like this. And sometimes you'll see your book reference it like that, where it's talking about that it's a helium-4 nucleus, or 2 protons and 2 neutrons, so as a mass number 4, all being kicked off all at once. Now, this is whenever you have an atom that kicks off 2 protons and 2 neutrons to become more stable. If it's kicking off 2 protons, what's going to happen to the identity of the element? Right, it'll change. So for example, going back to radium and radon, that we started off with radium. So radium has 88 and radon has 86. This one started off with a mass number of, running out of air. I'm talking too quick. I need to breathe. I do have post-it notes in here. I just didn't put them in the proper spots apparently. Alright, so we started off with radium 226, and then we had radon 222. So for this one, this substance, whenever it changed from this substance into this substance, it kicked off 2 protons, and then it also lost 2 neutrons. That's why for this first one, I should have left them. I'm sorry. I already broke my chalk today, so it's sad. So remember, for this first one, we said that there was a number of neutrons of 138, while the second one had a number of neutrons of 136. So, looking at these 2 elements we've already talked about, this one lost 2 protons and 2 neutrons. So, its mass number dropped by 4. This one it has 86 protons. So we'll go from this substance to this one would be an example of an alpha decay because it lost 2 protons, lost 2 neutrons, so it had a drop of a mass number by 4. So make a note of that for alpha decay. So this is whenever it goes from one substance to another and it's kicking off 2 protons, so the atomic number is going down, but since it's losing 2 neutrons as well, the mass number will drop by 4. Your book gives you an example of uranium-235. Hold all this one off to the side and try to not drop everything. That for this one, you get an example of uranium. Let's see, uranium-235, and it has the atomic number of 92. Whenever it goes through alpha decay, it becomes thorium-231. I don't remember what thorium's atomic symbol is. Pretty sure it's TR. Yeah, TH. Alright, so again, the mass number drops by 4 and the atomic number drops by 2. And remember, because you're dropping protons, you're changing from one whole element into another. So that's alpha decay. Beta decay, that's whenever a neutron changes into a proton, but remember, neutrons are neutral. So whenever they change into a proton, they will kick off an electron to balance out their charge change. So your book points out, whenever you have the atom's nucleus changes into a proton and it kicks off an electron, we call this a beta particle. So again, beta, the symbol for it looks kind of like a bee with a tail. So that's the best I can do to draw it. So beta looks like a bee with a tail, and it'll kick off an electron or a negatively charged substance to balance out its change from a neutron into a proton. So your book gives you the example like for carbon-14. So remember, carbon-14. How many electrons does carbon have? You might memorize this by this point. Right, 6. So whenever you have carbon undergo beta decay, you have a neutron change into a proton. So if you have carbon gain a proton, is it still carbon? Nope, it's nitrogen at this point because nitrogen has 7 protons. Now, if I have a neutron change into a proton, does the mass number change? No, because remember the mass number is number of protons and neutrons together. So the mass number is still 14, but it's kicked off an electron to balance out that charge for it. So make a note for it, make a note for this for beta decay, that you're going to have the atomic number increase by 1, but the mass number doesn't change, it stays the same. And it also kicks off an electron. So make a note for all that for beta decay. Gamma decay is a little bit easier. We have the, looks kind of like a Y. I'm going to draw it over here. It's kind of like a funky looking Y for it. It has a little bit of a swirly tail. So make a note, so Y or gamma decay, this is whenever you have an excited or an unstable nucleus, it releases energy, but it doesn't change the number of protons or neutrons. So make a note for this one, it releases energy without a change in the number of protons or neutrons, so the atomic number and the mass number doesn't change. But this energy is released as gamma radiation. This is extremely high energy waves. So these are electromagnetic waves of extremely high frequency and energy. So these are energy waves, and they have a lot of energy. So your body can't really absorb that very well. So your book points out talking about the dangers of them. So health effects of radiation. In large enough amounts, all 3 major forms of radiation are dangerous to you. Alpha radiation, this first one, if you have an alpha radiation hit you, typically your skin is enough to absorb it, and typically you will be fine. You can be exposed to alpha radiation in small amounts and you'll be okay. Now, if you swallow a radioactive particle that's giving off alpha radiation, because it's going through your entire intestinal tract, now you have an issue because your skin typically is thick enough to stop it. Your intestinal tract is not designed to absorb radiation, so you need to go to the hospital. You need help because it's not designed to basically shoot alpha particles into your digestive system. It's not designed to do that, and you need to go get help. Beta particles, your book points out as well, are somewhat more dangerous because they can go deeper into your body. so they can get through your skin and get into your tissues, but again, not necessarily super dangerous. I mean, you don't want a bunch of it, but you got to be careful for it. Gamma radiation is the most dangerous though, because it can go all the way through your body. Now, you might think, okay, well, gamma radiation, that's extremely tiny, right? So this is smaller than an electron. So how dangerous can it be? It's like the idea of having a bunch of little lasers go through you. Now, it might be tiny little lasers, but if you get a bunch of tiny little holes, your body's in trouble. So that's the idea of gamma radiation. It's tiny, 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 but if you have a bunch of it go through your body all at once, it's not good for your body, and your cells can't handle that, and they can't deal with that. So that's part of the reason as to how come all three of these radiations are dangerous. Now, in small amounts, you're okay, but too much of it, for any of them, is not good for you. But the most dangerous one is radiation. That's part of the reason why people, whenever they talk about radiation shielding, typically they mean the gamma one, because the gamma is the most is the most dangerous, that it can go through the most stuff. All right. So your book points out that research indicates though that radiation can cause harm, only relatively large amounts of damage. So your book points out that your body naturally heals itself from radiation. Look at the chart where it talks about the average annual radiation exposure. Most of the radiation exposure we get is just from the earth, like radon gas. Radon gas is radioactive, and so because of that, you just get that from the earth. The earth is a radioactive planet. In some cases, you get it from medical procedures, like once a year, you probably have your teeth x-rayed. Well, that's typically not enough x-ray or not enough radiation to like hurt your head or hurt your body. That's the reason why though, if you ever wondered, whenever someone is taking an x-ray, why does the nurse or the dental hygienist leave the room whenever you're being x-rayed? If it's so dangerous, why is she leaving? It's because she takes a lot of x-rays, and if she were to stand in the room with all the x-rays, that would be too much radiation for her body. So she might get hurt long term if she were to stand there and be exposed to radiation over and over and over and over again. That's why she leaves the room typically. You're only getting it one time, typically once a year, and so because of that, that's not enough radiation to really hurt you. Think of it as kind of like a sunburn. You go outside in the sun probably every single day. If you don't go out in the sunlight every single day, that's a little bit of a concern. You need to go out and get sunlight. But you go out typically every single day. Now, if you go out too much, you could get a sunburn. Now, that's too much sun exposure all at the same time. And that's the idea with radiation. If you get a little bit of radiation, most of the time, your body can handle it. You're exposed to radiation from the earth. If you look at the chart, you'll also notice that even the human body is radioactive. You're giving off a little bit of radiation right now. Your sibling sitting next to you at the table or at the desk or wherever you're at the house is giving you a little bit of radiation. So you can turn and glare at them really quick because they are currently infecting you with radiation just by sitting there. But your body is fine. You're going to be okay with it. Your body can absorb a little bit of radiation and be just okay. Now, if you get too much radiation all at once, now that's a problem, and now it's not safe for you. So, your book points out, though, that, okay, radiation in small doses, because we get it from the earth. Your book points out solar flares, we get it from sunlight, we get it from other people, that a little bit of exposure is fine. It's whenever you have too much exposure, now you're not fine anymore, and now you might be in trouble, and you might need some help. Your book points out that there are several good uses of radiation, though. There are two major reasons. So, nuclear medicine. This is the use of radioactive substances to diagnose or treat cancer and other diseases. You might know someone who's gone through chemotherapy. That's typically what chemotherapy is. Now, there's different types of chemotherapy. But if someone is going through chemo, that's what they're using radiation to try to kill off the cancer cells in their body. Now, your body cells can get shot with gamma radiation or different types of radiation. And your body cells, it'll make them sick and hurt them, but they'll survive. Cancer cells don't have that ability to survive very well, so because of that, they'll use chemotherapy to try to kill the cancer cells, but leave your body cells intact. That's maybe a reason why if you know someone who's gone through chemo, their hair might fall out and they might lose their hair because their body is basically fighting through the trauma of getting shot with gamma radiation or alpha radiation or beta ray radiation. And since your body has been shot with radiation, it's trying to fix itself, so it might do some things a little bit differently until it's done fixing itself. That's one reason why someone might be sick the next day after going through chemo, is because their body is trying to fix the insides now. Now, the cancer cells, they can't do that. The cancer cells, if they get stabbed with radiation, the cancer cells can't really survive very well. So also we use chemo to kill off the cancer cells. That's one of the best ways we know to fight cancer. So that's one reason why radiation is good, is we can use it to help save someone's life that has cancer. Another good use of it is food irradiation. Now, your book points out as well that in some cases foods are sterilized by exposing them to gamma rays. So they'll shoot food with gamma rays. Now that doesn't make the food radioactive. Now, a lot of people assume that. Now, the gamma, once it goes through them, it's done at that point. But it'll kill off any parasites or bacteria on the inside, and it'll leave the food tasting okay on the inside for it. So that's one reason why they use gamma radiation for it. We also use it to sterilize really sensitive equipment. So it's used to sterilize first aid kits, adhesive bandages, other medical supplies. Like if someone is going into surgery, they will use sterilized instruments because they're taking a knife and cutting open a person. You don't want any type of bacteria or viruses on that knife. And so because of that, they will use gamma radiation to make sure everything is dead. There is nothing on it. It is entirely sterilized. If they just washed it in a sink, there might be residue of something on it. So they use gamma radiation to make sure it's entirely clean before they work on someone to try to help someone. They don't want to accidentally introduce a virus or bacteria or something on the inside of a person's body. To make a note, there are several good uses of radiation, even though we know that radiation is dangerous and too much of it is not good for you. But your body can handle small amounts, and then there's several good applications of radiation as well. Alright, let's look at the neutrinos really quick on page 124. So let's read through this really quick because it is interesting, and then I'll let you go. Alright, so the electron and neutrino, commonly shortened to just neutrino, meaning little neutron, is one of the many interesting and puzzling subatomic particles. It is related to the electron but has no electric charge and almost no mass. Like electrons, neutrinos are thought to be indivisible. Because neutrinos have no electric charge, they pass through electron shells with atoms practically unaffected. They are deflected or absorbed by the atom only if they collide with the nucleus itself. Because atomic nuclei are small, such collisions rarely occur. In fact, neutrinos can pass virtually unimpeded through the Earth itself. The fact renders neutrinos inherently difficult to study. These are very tiny substances, like an electron, but they don't have a charge. Neutrinos are thought to play a small part in nuclear reactions, though they themselves are not radioactive. The existence was proposed by scientists in order to explain an apparent mass loss during beta decay. Later, scientists discovered that the sun, operating through a massive nuclear reaction, produces large amounts of neutrinos which stream virtually unimpeded through the sun's outer layers, the Earth, and our bodies without significant effects. Scientists believe that collisions with neutrinos can cause nuclear reactions in atoms that are normally stable. If a neutrino collides with an atom's nucleus, the neutrino may be absorbed by a neutron. The neutron releases an electron and becomes a proton in a reaction similar to beta decay. The extra proton changes the atom into an element with an atomic number 1 greater than the original element, while the mass number remains unchanged. For example, a neutrino can change an unstable chlorine-37 atom into an unstable argon-37 atom by changing a neutron into a proton. The extra electron is produced is captured by the atom to balance the charge. Because a neutrino rarely gets a chance to interact with other matter, however, this type of reaction is rare. So just make a note over what a neutrino is, how it's like an electron, but it's neutral. So it's very, 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 very small, and and as far as we know, it's neutral. Because they're so tiny, and since they don't have a charge, they're very difficult to study. So your book's just pointing out that, hey, if you go into higher chemistry fields, you're going to have references to this, and occasionally you come across this online. So because of that, your book is introducing it to you. So make a note, a neutrino, it's like an electron, but it has a neutral charge. As far as we know, that's what it is. But maybe in a decade or so, we'll have a better explanation for it. Alright, well go ahead and we'll stop there. Your homework for tonight, read pages 129 up to 132, 129 up to 132, answer on page 130, question 7 now, and on page 134, 1 through 5. So, answer on page 130, question 7, and on page 134, questions 1 through 5. Don't forget, hopefully the background paper is due Monday because y'all will be back in school, but it's due the first day that you're back, so don't forget about it. So, your page 129 through 122, answer on page 130, question 7, and on page 134, questions 1 through